Welcome back to the deep dive. Today we're jumping into something pretty fundamental in manufacturing, making that call between high-speed wire EDM or HS-WEDM
Oh, yeah.
and its, let's say, more precise sibling, the medium-speed machine, MS-WEDM.
Yeah, it's a choice that, well, it can really impact your bottom line. Get it wrong. And you could be looking at parts that just aren't up to scratch, maybe huge rework costs, or maybe you've bought a machine that's just, too slow.
So our mission today is really to cut through that confusion. We want to give you the specifics, the mechanics, the business side of things for each one, hopefully saving you some expensive trial and error down the road.
Exactly. We want to shortcut that learning curve.
Okay, so let's maybe kick things off with the quick answer, the sort of cheat sheet.
Mm.
If you're mainly doing general fabrication, maybe lots of roughing work, functional parts where, speed is key and cost is a big factor.
And the tolerances are a bit looser, say plus or minus 0.01 in millimeters.
Right. If that sounds like your shop, then the high speed, the HS-WEDM, that's probably your workhorse.
But on the other hand, if you're dealing with clients needing really precise molds, complex dies, maybe parts for aerospace or medical, stuff that needs an almost mirror finish and super tight accuracy.
Like down to plus or minus 0.005 millimeters.
Yeah, exactly, that kind of precision. Then you really have to be looking at the medium speed, the MS-WEDM. That becomes the strategic investment.
And what's really interesting, I think, is how these two relate. The MS-WEDM, this precision machine, it didn't just appear out of nowhere, did it?
No, not at all. It's basically an evolution. It was developed specifically to fix the inherent shortcomings of that original high-speed process.
So understanding that original problem, that limitation, is kind of key to the whole decision.
Absolutely. If you strip it all back, the fundamental difference, the thing that drives everything else, is surface finish. I mean, that's the entire reason MS-WEDM machines were even developed, to get a better finish than the high-speed ones could offer.
Okay, so let's dig into that. The original, the HS-WEDM, the workhorse, how does it actually work? What's happening mechanically?
Well, it's pretty straightforward, really. It uses a single cut, basically a high-energy electrical discharge, to zap through the material fast. And the key thing is the wire, usually molybdenum wire.
Molybdenum, okay.
Yeah. And it gets used over and over again. It runs back and forth, reciprocating. At really high speeds, we're talking, 8 to 12 meters per second?
Wow, okay, that's moving.
It is. And that speed, combined with the fact the wire is constantly reused, well, that's also its limitation when it comes to quality.
How so?
Think about it like maybe a power saw versus a very fine scalpel. Because that wire is zipping back and forth and being reused, it starts to erode a tiny bit over time, and it vibrates.
Ah, vibration.
Exactly. That vibration, plus the high energy of that single cut, it directly causes a rougher surface finish.
And we can measure that roughness, can't we? Using raw values.
We can, yeah. Raw or roughness average. It's basically a measure of how bumpy the surface is. For a typical high-speed machine, you're looking at a raw somewhere between, say, 2.5 and 3.2 micrometers.
Which sounds small, but in machining terms.
It's actually quite rough. Visually rough, functionally rough. If the part needs to look good or fit precisely, you're almost always forced into doing extra work afterwards. Polishing, grinding, expensive manual labor, every time.
Okay, so HS-WEDM is the fast, somewhat rough power saw. What about the MS-WEDM, the finisher? It uses molybdenum wire too, sometimes, right? But the process is different.
Fundamentally different approach. It's about refinement. Instead of one big blast, it uses a multi-pass strategy. So it'll do one initial roughing cut, kind of like the high-speed machine does.
I get the bulk of the material out.
Exactly. The heavy lifting. But then it follows up with more passes, a second, maybe a third, sometimes even a fourth pass. These are called trim passes.
Trim passes, okay. And these aren't just repeating the same cut, are they?
No, that's the clever part. Each trim pass uses progressively lower electrical energy. Think of it like using finer and finer grades of sandpaper. They're designed to just skim the surface.
And what are they skimming off?
This is crucial. They remove something called the recast layer.
Recast layer. Okay, maybe unpack that for us. What is that?
Sure. So during that first high-energy cut, some material melts, but doesn't get fully flushed away by the dielectric fluid. It then re-solidifies onto the cut surface. That's the recast layer. It's brittle, uneven. Basically, it's junk you don't want on your finished part.
Right.
The MS-WEDM's trim passes, because they use such low energy, they're just enough to vaporize away only that rough recast layer, leaving the clean, undisturbed metal underneath.
Ah, so it's like a very precise cleaning operation electrically.
You could put it that way, yeah.
Yeah.
And the result is dramatic. That roughness value, it drops way down. We're talking typically zero point 0.8 to 1.2 micrometers, maybe even better, straight off the machine.
From around 3 down to potentially under 1, that's a huge difference in smoothness.
Huge. And that smoothness, that finish, that translates directly into value, into profit, especially in certain industries.
Which brings us to the high-value work. Why is MS-WEDM basically the minimum standard for things like mold making or precision dies, aerospace parts?
Well, it connects directly back to what those industries are buying. They're buying surface integrity. They're buying dimensional certainty.
Take molds, for instance. The surface you machine into the mold becomes the surface of the plastic or metal part that comes out of it, right?
Exactly right. It's a direct transfer. If you have a rough mold cavity, maybe from a high-speed machine without finishing, you're going to get a rough part. And that part will likely be rejected. You need that near-mirror finish in the mold itself.
Makes sense. And you mentioned dimensional certainty. That links back to those tight tolerances, the plus or minus 0.005 millimeter.
It does. And achieving that reliably comes down to minimizing something called the HAZ, the heat affected zone.
Okay, HAZ. Let's talk about that. Sounds important, especially financially.
It really is. The HAZ is the zone next to the actual cut. It didn't melt, but the heat from the electrical discharge still affected it, changed its properties slightly, induced some stress. Now, in materials often used for high-value tooling, like hardened tool steels, these things can cost a fortune and take weeks to machine. Excessive heat and stress in that HAZ can cause the material to distort or warp.
So even if it looks right coming off the machine, it could actually change shape later on, maybe after heat treatment or even just sitting on a shelf or worse, in service.
Precisely. That's the nightmare scenario. You could lose tens of thousands of dollars, weeks of work, just like that. Catastrophic.
Wow.
The MS-WEDM, with its low-energy trim passes, drastically reduces the size and impact of that HAZ. It gives you much better dimensional stability over the long term.
Wow.
Less risk.
And less risk means less cost, ultimately. Plus, you mentioned the labor saving.
Yeah, that's a huge factor, too, because the finish from an MS-WEDM is often good enough straight away. You might completely eliminate the need for that secondary polishing or grinding.
Which can take hours or even days of skilled labor, right?
Absolutely. Highly skilled, expensive labor. So when you factor that saving in, suddenly the higher initial price tag, the MS-WEDM, starts to look a lot more justifiable, doesn't it?
It really does. But okay, we shouldn't just write off the HS-WEDM. You called it a workhorse. It clearly has its place.
Oh, absolutely essential. We need to be clear, it's not a bad machine. It's an incredible machine for the right jobs. Its strengths are its speed, its simplicity, and crucially, its operating cost. Let's talk about that reusable molybdenum wire again.
Right. You mentioned it's reused. How does that compare cost-wise to, say, the wire used in the even higher-end true precision WEDM machines? They often use brass wire, don't they?
They do, and those top-tier machines typically use that brass wire only once. It goes from the spool through the cut and straight onto a scrap take-up reel. Brass isn't cheap, and you're constantly consuming it.
Okay.
The molybdenum wire on an HS-WEDM, however, can be used for 10, sometimes hundreds of hours. It just keeps running back and forth. That dramatically slashes your consumable costs, makes the HS-WEDM a real champion for cost-sensitive, high-volume work.
So where does it really shine? What are the specific applications beyond just, say, quick prototypes?
General fabrication is a big one, making jigs, fixtures, test parts where the final finish isn't the most critical factor. Speed and cost are paramount there.
Okay.
But also, strategically, even high-precision shops use them for roughing. They'll take a big block of expensive material, use the fast HS-WEDM to chew out the basic shape, get rid of maybe 90% of the waste material really quickly.
The heavy lifting, as you said.
Exactly. And then they move that roughly shaped part over to their slower, more precise MS-WEDM, or even a high-end machine for just the final critical finishing passes. It's about using the right tool for the right part of the job to maximize overall shop efficiency.
That makes a lot of sense. A kind of hybrid approach. You also mentioned specialty materials earlier.
Yes, that's another interesting niche because WEDM is a non-contact process. It's electricity doing the cutting, not physical force. It's great for materials that don't like mechanical stress. Think really thin-walled parts that might bend or deform easily with traditional milling, or composite materials like carbon fiber. If you try to machine carbon fiber mechanically, You risk delaminating the layers.
Ah, pulling the fibers apart.
Right. But WEDM cuts cleanly through without applying that mechanical force, so it preserves the structural integrity. Very useful for certain aerospace or automotive applications.
Okay, this is great. We've got the mechanics, the quality differences, the applications. Let's get really practical now. Let's focus on the investment decision itself. Someone's got the budget, they need a machine. How do they actually choose? It sounds like it's less about the tech specs and isolation and more about
Wire.
their customers, their business goals.
That's exactly it. You have to look beyond just the machine's capabilities and think about the work you need it to do, the customers you serve, and where you want your business to go. We can probably boil it down to maybe 5 key factors to consider.
Okay, a checklist. Let's hear it. Factor 1.
Factor 1 has to be precision and tolerance. Be honest with yourself. Is plus or minus 0.01 millimeters genuinely good enough for the vast majority of your work? If yes, the HS-WEDM is very attractive from a cost perspective. But if your contracts consistently demand a tighter plus or minus 0.005 millimeters, or even better,
Then the MS-WEDM isn't just nice to have, it's basically mandatory.
it's a gatekeeper to that kind of work. Simple as that.
Okay, factor 2.
Surface finish and rework. This hits the labor cost directly. Are you set up and are you willing to absorb the cost of secondary finishing, the polishing, the grinding for parts coming off an HS-WEDM? Or do you need parts to come off the machine ready to ship or ready for the next minimal process step with that right below, say, 1.2 micrometers?
Because if you can eliminate that manual finishing,
The higher upfront cost of the MS-WEDM can pay for itself pretty quickly in saved labor and faster overall turnaround. It becomes an operational saving.
right, factor 3.
Production speed versus quality focus. We know the MS-EDM is inherently slower per part because of those multiple trim passes. So what drives your revenue? Is it pushing out the maximum volume of relatively simple parts as quickly as possible? That favors the HS-WEDM's throughput.
Or is your business built on delivering the absolute highest quality and accuracy on complex, high-value components, even if each one takes longer?
Exactly. That's the MS-WEDM focus. You have to be really clear about which metric speed or single part quality is more critical to your profitability.
Makes sense. Factor 4 is probably the big one, budget and costs.
Always is. The HS-WEDM clearly has a lower initial purchase price. And as we said, the running costs are lower because of that reusable wire. Much lower consumables bill.
Whereas the MS-WEDM is a significantly bigger chunk of capital up front.
It is. So you have to run the numbers. Calculate the return on investment. Does the ability to command higher prices for precision work, plus the savings from eliminating rework, plus the reduced risk of scrapping expensive parts due to HAZ issues, does all that offset the higher initial investment?
And sometimes the cost of just one major failure, one warped mold, costing tens of thousands could have paid the difference between the machines.
That's often the calculation, yes. The cost of not having the precision can sometimes be far higher in the long run.
Okay. And the final factor, number 5.
This one's more strategic, future growth and market positioning. Where do you actually want your business to be in, say, 5 years? If the plan is to stay competitive as a general job shop, focusing on speed, volume, and cost effectiveness.
The HS-WEDM fits that model perfectly.
It does. But if your strategic goal is to move up the value chain, if you want to seriously compete for those high-margin, high-precision contracts in aerospace, medical, top-tier mold making,
Then the MS-WEDM isn't just a machine, it's an enabler. It's the key to unlock those doors.
precisely. It's a strategic investment in the kind of work you want to be doing. You need to be really ruthless about that market position goal to justify the spend.
Okay, fantastic. So wrapping up this deep dive then, the core message seems pretty clear. HS-WEDM, great for speed, volume roughing, where cost is critical and tolerances are a bit looser. It's your cost-effective workhorse.
And MS-WEDM. That's the necessary investment when you absolutely need top-tier accuracy, that fine surface finish, and the dimensional stability required for the most demanding industries. It's about precision and reducing risk.
It really is that classic trade-off between speed and ultimate quality.
It is. But, thinking about that trade-off raises a final point, maybe something for you listening to mull over.
Ooh, go on.
Well, we talked about how fast and cheap the HS-WEDM is for roughing, right? For just getting rid of bulk material. And we know the MSCVD excels at the fine finishing.
Yeah.
So instead of thinking either, should shops aiming for the absolute peak of both efficiency and quality maybe consider a strategy of always using both? Use the HS-WEDM purely as a super fast roughing tool, and then dedicate the MS-WEDM only to those critical, value-adding finishing passes.
Ah, so optimizing each machine for what it does best, in sequence.
Exactly. Could that kind of integrated workflow, leveraging the strengths of both technologies in tandem, actually be the smartest way to maximize both throughput and quality? Rather than compromising by relying solely on one machine type? That might be where the real competitive edge lies.